Hello, welcome to my tech farm. Approximately half years ago, I presented Extrudr PETG, PCTG, even carbon fiber PETG filaments. And actually, in the same time, they sent me these 4 filaments. So I will present in this video all 4 TPU filaments. A little bit I forgot about them, so that's why I present them now half years later. So I have here Flex semi-soft. The hardness of this filament is 85A on short A scale. And then Flex Medium, which has a hardness of 98A on short A scale, which is a little bit interesting. So medium, but basically this is the hardest TPU filament I tested on this channel so far. But again, we have here Flex Hard, and it is not even measurable on short A scale, so it has the hardness of 58D on short D scale. Here you can see the comparison chart or something like that. And also I have a Flex Hard, but reinforced with carbon fibers. And for this, it is recommended to use the hardened nozzle, of course, but also 0.5 millimeters or bigger. Well, I don't have 0.5 millimeters, so I will print it with 0.6 millimeter nozzle. Similar nozzle is recommended with that carbon fiber PETG filament, and I was experimenting. I tried to print with 0.4, and after approximately 10 hours of printing, I had the clog on that nozzle, so I will not experiment this time. So 0.6 millimeter hardened nozzle I will use with this filament. And don't forget, with TPU filaments, usually it is recommended to use some kind of direct drive extruder. And now the carbon fiber version, and the only printer where I have a 0.6 millimeter hardened nozzle is this, and also it is bimetal, CHT bimetal, so basically I don't have to raise the temperature. But anyway, I will start with the temperature tower from 260 down to 230 degrees Celsius. And interesting to see that how small is this half kilogram spool. It would be good to see some recommended print temperatures here on the spool too, just a reminder in the future. Interesting to see that it is completely flexible, so it will not break, but I don't feel at all that it is elastic. So this may be a good filament for the timing belt. You know, I have that video separately, I tested this, but let's finish this one, so that is the subject for the future. Starting with the tower from 260 down to 230. It's a little bit hard to see, but the start is good. I'm expecting a little bit more stringing here because this is 0.6 millimeter nozzle and the TPU filament. I left the default 0.8 millimeter retraction length, but we will see if it is enough. This is satin Prusa sheet, and the temperature on the bed surface is 40 degrees Celsius, and I believe this will be enough. I can hear some cracks from time to time, so this means that this is not completely dry filament. Well, the TPU absorbs moisture, and it is more than 1 year old filament almost, so definitely, probably I should dry it before I continue with the using. Also, I noticed the part cooling fan is not working, so I will add some part cooling to it. According to the website, the cooling should be between 10 and 30%. This is my first time I'm printing TPU with 0.6 millimeter nozzle and 0.3 millimeter layer height, and definitely I don't have good profiles for this, and this needs much more experimenting. You don't like the bridging, quite a lot of stringing. In the meantime I place it into filament dryer, but of course it will be dried in a couple of hours only. The sticking is okay, it could be better, maybe I will raise the temperature, but the print quality is definitely not acceptable. I'll try to reprint at least one element on 250 degrees Celsius, but with 0.2 millimeters layer height. I am reprinting one element on 250 degrees Celsius using the PETG profile, because Prusa is very good with the PETG materials. These parts are also from PETG. And I'm using 0.2 millimeter layer height in this case, and the printing is faster too. Only thing I change is the bed temperature, which is 50 degrees Celsius. Still not perfect, but definitely much better than this one. Surface quality is also very good, only I couldn't get rid of that stringing. Maybe I will try one more time, but this time I will raise the retraction a little bit. Definitely the stringing is reduced, not perfect, but these will be my settings for the test specimens. The start is good. I'm printing all test objects at once on 250 degrees Celsius, and I dry a little bit the filament, and I'm still printing from the filament dryer. Interesting, the printing is at 50% approximately, and the stringing almost completely disappeared. Of course, I'm still printing from the filament dryer, but this is a very pleasant surprise. The printing is at 80% and it will be finished in half hours, and I can see a few strings here and there, but that's something what is easy to clean. And even the surface quality was improved, so I will analyze this later. It's printed and only here I have a little bit more stringing, but others are acceptable. And it's very easy to remove them now when the plate is cooled down. GT2 timing belt, and I already have a separate video about it, and this one I need for some future testings, but of course depend on the results from this video. And I didn't know that it is printable with 0.6mm nozzle. End of the filament locked, and it goes to the vacuum bag with some desiccant inside. In the meantime, I assembled the Prusa MK4 and I'm curious how it performs with the flexible filaments. I will start with this Flex Hard, and I'm sure that it will not have a problem with this one here, but according to the social network chats, I'm expecting some problems with the software versions, but we will see that soon. Let's see if it will load it without problems. And it's extruding on the other side, so no problems with this hardened version, but I could hear some small micro cracks, so I believe that under this 1 year it absorbs some moisture. We will see, maybe I have to dry this too. The start is great, there is just a little bit more stringing, but the first layer lays down perfectly. Definitely I can recognize those micro cracks, so this filament has some moisture in itself, and we will see after this temperature tower if it needs some drying or not. Taking a closer look of this temperature tower, the overhang is okay. I think not the stringing but the bridging is biggest problem here, but it depends a lot from the settings. And I think just a minimal drying and I can print everything on 250 degrees Celsius. Great first layer, but I can see that I will have few strings between the objects. The printing is at 65% and I think this amount of the stringing is acceptable, but definitely if I would dry it more it would be better. And I use the filament dryer only before the printing. Printing is finished. Well, there is some stringing, it has to be cleaned, but the objects are usable. And now moving to the flex medium, and I'm not expecting problems here yet because this is still quite hard. 98 on Shore scale, and the temperature tower will be from 250 down to 230 degrees Celsius. And this time I will dry the filament more seriously, so more than 4 hours of drying, and after 2 hours I'm rotating the spool so it will be dried more equally. And the temperature inside is approximately 50-55 degrees Celsius, but for TPU filament we don't even need more. And now let's see the loading of new filament. Temperature tower from 250 down to 230 degrees Celsius. The first layer looks good, only it's a little bit hard to see on the camera because of this dark blue color. In theory I should have more stringing problems here compared to the previous filament, but it is cleaner here. The other problem I can see is the bridging currently on that highest temperature element. So definitely those 4 hours of drying helps. And finally I could catch the bridging moment. And here you can see the problem, this bridging is too big. The small bridging came out correctly. Great overhang and actually almost no stringing. So the only problem here is that bridging. But with the test estimates I don't have the bridging problem there, so I will again print everything on 240 degrees Celsius. The first layer is almost finished and it looks amazing. Almost not even one string I can see here. So definitely that drying helps, and immediately I will place in the filament dryer the next filament, which is the soft one. The printing is at 80% and still no stringing, so this is very promising. Printing is finished and only here a few strings appeared, and I'm quite sure that it would be better if I would print from the filament dryer too. And after 4 hours of drying, it's time to print with the flex semi-soft filament. And now let's see the loading. Okay, the filament is on the other side of the nozzle. And now I'll print the same temperature tower like with previous filament, from 250 down to 230 degrees Celsius. I'm not going down to 220. It's a little bit hard to see because this is transparent color, but the first layer is okay. I want to show you this. So all this mess you can see on the first element is basically because of the failed bridging, but actually there is no stringing, and this you can see on this second element. And this is that bridging moment. And again, when it is a long bridging on this side, it fails. And interesting to see that even the bridging was successful on the last element, but all test objects are printed on 240 degrees Celsius. And interesting, maybe the softer filament is even nicer. Printing the same G-code like with the previous filament. This is now the third layer, and maybe I can see 1 or 2 strings, so it will be okay. Interesting to see, the printing is at 60% and it is very clean. Those 2 strings I mentioned were only in the first and second layer. Everything is printed. And now this filament goes to the reusable vacuum bag, something like this. But there'll be one more printing. If you remember, I had a filament which was full of moisture. It's in a filament dryer 5 hours now. And now we reprint just one element of that temperature tower. It's a bridging moment, and as you can see, almost no stringing on this element, only this ugly bridging will be visible. And these are 2 same elements, and I hope it is visible on camera too. So here I have a lot of stringing, and here almost no stringing at all. That failed material is only the bridging. So definitely the drying really helps with TPU filaments. I will start with a little bit new thing because I got this request several times. It's a friction test. This will not become a regular testing method, but I became curious, and since here we have different hardness of the TPUs, it will be great comparison. So I have this plate, and I will place here exactly 2.5 kilogram load, but together with the plate the load is 3.5 kilograms. And then I will measure the pulling force, actually the load, with this hanging scale. And I will do it in the different materials. So I will do it on this desk, and then I will do it on the glass and also on our floor, and then we will see what kind of friction we have with the different legs. I already know that this will be very long video, so I will show you only one pulling for each material on one surface, but I will do all 36 measurings. Hard carbon fiber, 0.7, 0.72, 0.69. 0.93, 0.81, 0.8, 0.79, 0.78, 0.73, 0.79, 0.88, 0.86. Just quick conclusions for the end. If this became my regular testing method, it will be only on the glass, because I noticed I got most constant results on the glass because the surface is more equal. Now, what is your opinion about this? Should I include this in my future TPU testing videos? This is the pulling test where I want to record the brake load, but also I want to record the maximal length before the brake. And now this is the hard without carbon fibers. The medium, and it failed inside the test objects, and very similar failure I can see on the semi-soft. On 2 soft materials the inner wall snapped first, but on carbon fiber version it broke completely on the smallest cross-section area. And now the layer adhesion test with vertically printed object, and it is interesting to see some elasticity before the break. And also in this case the smallest cross-section area is 4 by 4 millimeters. As you can see, each object broke correctly on the smallest surface. This is the ring test where the test object will get some compression and bending stress. The load will be 1.25 kilograms, and I'm measuring the deformation. This is the initial deformation. This is after 1 minute. And this is after 2 minutes. And when I remove the load, it is hard to see visually any permanent deformation on these test objects. And now this new ring has the same dimensions like the previous one, but this time it will get some pulling and bending stress. The load will be again 1.25 kilograms. And the initial deformation I am measuring first. This is the carbon fiber version. And then after 2 minutes. Without load, the diameter is 50 millimeters. And now this is the hard without carbon fibers. Side by side it's a little bit faster. This is the medium. And this is the semi-soft. Here you can see some deformation when I place the load. And side by side, initial and after 2 minute deformation. And the same thing here, when I remove the load, it is hard to see any permanent deformation on them. And now my washer test. These are M6 bolts and I will do exactly 3 rotation. And then I will measure the maximal torque for this. This is the tightening torque. This is the first test object and this is the second one. This is the carbon fiber version. And now this is the hard but without carbon fibers. This is the medium, and interesting, this was bigger than the hard, the maximal torque. And this is the semi-soft version. Now I was confused, why is the medium stronger in this case compared to the hard? So I analyze the footage. So this is the first rotation of the hard, the second one and the third one. So I can see that almost linear increase. And this is the medium, the first rotation, the second one and the third one, and I got similar results with both test objects. So these are the results. So now I'm waiting 1 day, and after 1 day I am measuring the untightening torque. This is the carbon fiber version, the hard version, medium, and this is the semi-soft. 0.7. Here I'm measuring their permanent deformation after half hours. The original length is 15 millimeters and they were compressed 3 millimeters for 1 day. I will show you the numbers in the results part. This is my creep test for the TPU filaments. The thickness of this test object is 0.8 millimeters and the load is 1.25 kilograms. And even now I can see some difference in the deformation. And I'm measuring this deformation. This is the initial, the first day. And I measure them every day. This is the last day. I already measured them, so I'm removing the load now. And I can see some permanent deformation on these test objects. The temperature test in the oven. These 4 on the left side are TPU filaments, and this is PCABS from my previous video. The temperature I will follow with this cooking thermometer, and I want to record the temperature of the first deformation. M10 nut as a small load is placed on these test objects. At the beginning no changes, and then the first deformation I noticed on the semi-soft filament, then on the medium, hard, and on the carbon fiber version I noticed the first deformation only at 150 degrees Celsius approximately, but even then the deformation was very minimal. And basically this is very similar to the given specifications by the extruder. So I can see some elasticity on each of them. And only after 2 minutes they all get back their own flexibility. And now let's analyze the results in this Excel table, which you can download from my techfun.com website. I'm starting with the creep test. These are directly measured values, but what we need is difference between 2 days, and that's what we can see in this table or on this graph. And here you can see that after day 1 we still have some creeping. The minimal is on the carbon fiber version. But after day 2, basically that creeping stopped with every material. On a tensile or pulling test, we can see that here the best was the hard carbon fiber version, but with the smallest elasticity. On the layer adhesion test, these are all acceptable values for the TPU materials, and it was very good to see that we have some elasticity before the break with each filament here. The ring test, with the bending and compression, and I measured here the deformation after 0, 1 and 2 minutes. And here the biggest deformation I can see with the semi-soft filament, but what is important here that this line here is almost horizontal. This means after 1 minute the additional deformation was very minimal. Something similar we can see on the bending and tensile ring test. Here the biggest deformation is on the semi-soft material, but here I measure only after 0 and 2 minutes. Now the washer test. For me, where I'm using the TPU materials, this is the most important test for me. And here we can see the tightening torque, and this is the untightening torque. Now for me the best is actually if the difference between two is not big. So perfect would be if the untightening torque is equal to the tightening torque. So basically from these four, actually the hard and the medium perform the best for my needs. And again, for me it is very important to see the deformation after 30 minutes without load. The default length is 15 millimeters, and unfortunately here more than 1 millimeter permanent deformation after 1 day when it was compressed to 12 millimeters. On the temperature test, they perform great actually, and each of them can survive even the boiling temperature. This may be interesting for some food safe applications, cleaning with the boiling water. And actually here the hard carbon fiber version performed the best, 150 degrees Celsius. That was impressive. And that friction test, well, on the desk and the floor, I don't really like this test because the surface is not completely smooth and sometimes it's stuck in some unequal parts. On the glass we can see that the softer material basically result better friction. Other three actually had very similar friction in this test. This Excel table I already mentioned you can download from mytechfun.com website. Every data is available for everybody, and for my Patreon supporters I'm preparing a new sheet where I will collect all results from TPU testings, because they can easily compare these results to those which I did in earlier videos. Basically this is my only gift to my Patreon supporters. About these filaments, the medium and hard are more or less similar to each other. The semi-soft is definitely more elastic compared to these three. Now, very pleasant surprise was this carbon fiber hard version, because very often I can see that adding carbon fibers to some material makes it weaker. Here it is not the case. Actually it was stronger in most of the tests. Of course we lose some elasticity, but for example very impressive was the layer adhesion test, where it was actually the strongest, or maybe the temperature test, 150 degrees Celsius, so that was also very impressive. Now, unfortunately, it can be printed only with 0.5 or bigger nozzle, and this is a problem because with the TPU we are expecting more stringing, and using bigger nozzle, this problem even more expands. Now, pay attention that the TPU filaments must be dried. But the good news is that actually almost any cheap filament dryers can do this job. 50-55 degrees Celsius is enough, 4, 5 or 6 hours, and you will get great dry material for the printing, and the printing quality will be definitely much improved. About printability, well, it looks like the Prusa MK4 did a great job. I was expecting some problems with the softest version, but it was printed correctly. Of course, don't forget you need a direct drive extruder for this printing. Don't print too fast. In my case, almost the PETG settings were great, only the bed temperature was maximum 40 or 50 degrees Celsius, depend on the build surface. But basically, with this, I had very nice printings in all 4 cases. Now, I'm still thinking to add some new types of the tests to this TPU experimenting. Maybe you can help me out a little bit. Where are you using TPU filaments? What are those applications? And maybe I will try to figure out some new types of the test. Until that, I hope I could help you with this video. Thank you for watching and happy printing.